As many of you know, for Bill's 60th birthday, a conference was held, in fact, jointly between the two of us. I mean, we've been close friends and colleagues for quite some time. I think this time the conference organizers realized that Bill is actually much older than me, so it'd be better to hold a separate meeting. However, I do want everybody to take note of the fact that this entire workshop is being held in the Bob room. Okay, well, what I'm going to talk about is, has to do with what people call the black hole information paradox. And, well, I'm going to give an basically updated version of a talk that I gave at a Santa Barbara workshop on this topic 2 years ago. Bill and I were both at that workshop. Bill gave his talk. I was after him on the program, and then as the questions were getting rather hot and heavy, claimed he had to catch a plane and left before hearing my talk on this. So I've been waiting a couple of years now for the opportunity to have a conference that Bill would be present at, where he'd have great difficulty pulling off that excuse again. Right? You don't have any plane this morning, do you? Okay, now at that meeting, there were about 75 or so participants, and if there was a vote on whether information loss happens in the process of black hole formation and evaporation, whether there is any information loss, the vote would have been, I'm quite sure had it been taken, well, 73-2, or possibly 72-1 with one abstention, depending if we caught Ted Jacobson in the right mood or not when the vote was taken. So it's really important to me that Bill and I and my views have really been in complete alignment over this whole period, because 73-2 is a lot better than 74-1, and so on. But that's actually a reason why I'm actually very worried about this talk. I mean, even though I think this audience is probably much more receptive to these, to the points that I'm making than perhaps most of the Santa Barbara. But I am very concerned because in my, much more than 30 years experience with Bill, I've learned that there's one and only one effective way to get Bill to change his mind, and that's to agree with him. So I'm a little worried because everything that I say here should be in complete agreement with Bill's views. Okay. So now let me explain the issue at hand, which has to do, well, with quantum entanglement. So I mean, just to, since there's some non-quantum GR people in the audience, I should really probably begin with, I mean, in quantum mechanics or quantum theory generally, I mean, if you have two systems that perhaps have interacted in the past, but are not, or let's consider the case where they're not interacting now. I mean, even if before the interaction, you started these two systems off in a product state, they're not going to stay in a product state under interaction. There'll be entanglement. The joint state of the system, as I say, can always be written as a superposition of product states, but won't itself be a product state. And in that kind of situation, you can't describe one of these systems alone by a state vector. You can certainly describe it as a density matrix. The whole system is still in a pure state in this usual quantum mechanical setting. But if there is entanglement between the two systems, meaning that the final state is not a product state, then you have this situation where a single subsystem by itself can't be described by a pure state. It would be mixed. Now this kind of entanglement is absolutely ubiquitous feature of quantum mechanics. I mean, if you have any two systems interacting, they will tend to get entangled, even if they didn't start out that way. But it's really an even more essential feature of quantum field theory. Specifically, here's a space-time diagram with some Cauchy surface drawn in, and I've just divided that arbitrarily into two halves. And if I consider system one, the observables in this space-time region, and system two, the observables in that space-time region, and these regions abut one another, they don't overlap, but so they're really distinct systems, then there will always, in quantum field theory, in any non-singular state, be strong entanglement between these systems. That's just the way states of quantum field theory are. For any physically acceptable states of the joint system will be strongly entangled. In fact, formally they'll be infinitely entangled. If you impose some Planck scale cutoff of some sort, you'll get a finite entanglement or whatever, but it'll be huge depending on what cutoff scale you use. So another way of saying that is that there are always strong correlations at space-like separations, at least at small scales. And this is very familiar with anyone who's studied Unruh effect or whatever. In particular, in Minkowski space-time, if I take these regions to be Rindler wedges, there's this strong entanglement, and that explains how the observers in, let's say, the right Rindler wedge see a genuine thermal state, which is very mixed. When the quantum field is in the pure vacuum state, that's because the right Rindler wedge state is strongly entangled with the left Rindler wedge. And so the description of the state on the observables in the right Rindler wedge is by a mixed state, which happens, in fact, to be a thermal state. Okay, well, the same thing happens in a space-time that has a black hole. So if you have and let me consider a situation which is, the physically relevant situation where you, don't start with the black hole, but you have gravitational collapse take place so that a black hole forms, then there's going to be entanglement in the same sort of manner between the state of the quantum field inside the black hole and outside the black hole. And this entanglement is, in fact, intimately related to the Hawking effect and explains, why the Hawking particles that reach infinity are in a mixed state, because they're entangled with degrees of freedom that correspond to what's inside the black hole. Now, one of the things I want to emphasize is that this isn't the only entanglement that takes place. I mean, you could, consider matter that's highly, two blobs of matter that have interacted in such a way they're highly entangled, pull them apart, collapse one of them, then again, the degrees of freedom inside the black hole will be highly entangled with the degrees of freedom outside the black hole, even not taking Hawking radiation into account. Okay, so if you take into account the Hawking radiation, you find that a flux of positive energy is going out to infinity, and nobody seems to dispute that idea. That's not anything that's being challenged. That being the case, there has to be a flux of negative energy going into the black hole, and that's totally consistent, although people have not been able to do full calculations of the stress energy tensor near the horizon of this dynamically evolving black hole. There's every reason, well, it has to be the case. There is a consistent theory of the stress energy, what the quantum stress energy would be in quantum field theory in curved space-time and semi-classical gravity. And it just, by conservation of energy, has to be the case that there's a negative energy flux going into the black hole. So if one takes back reaction into account, it's clear, and again, this is not especially controversial in any way, that the black hole is going to lose mass. And, well, if one believes it eventually loses all of its mass rather than caught at a Planck scale remnant or something, and I'm going to get back to that point, then the black hole would eventually evaporate completely, and if you, to the extent that you can represent what's going on with a classical GR space-time diagram, the space-time diagram would look like this. And when one sees this sort of diagram, and you know, very commonly in papers written after 1974, where you've got a black hole that forms by collapse, it Hawking evaporates and then disappears. So the story then with respect to information loss, the issue is the following. We certainly could have started down here with some pure state of the universe before gravitational collapse. And when collapse, you know, after the black hole has formed, we're certainly going to find entanglement between the inside of the black hole and the outside of the black hole. The Hawking radiation itself is associated with that entanglement. There'll automatically, just for any quantum field state, be a lot of short distance entanglement across the horizon, just like there's a lot of short distance entanglement between here and there. And furthermore, as I say, we could have entangled things at early times between here and some other stuff out there. That will be there. But the entire state of the universe on this slice will remain pure. The state on observables outside the black hole, of course, will be mixed because of this entanglement. The new feature that occurs with the black hole evaporation is that after the black hole has evaporated, there's no more, I mean, the stuff here is still entangled with the stuff there, but there's no more there up here at this time. So if you just look at the state here, that will describe a mixed state, and you will thus have evolution from a pure state to a mixed state. And this phenomenon is what's referred to generally as the black hole information paradox. So there's absolutely no question that in the if I give you a space-time of this sort, and we do quantum field theory in curved space-time, then the final state is going to be mixed, and you're definitely going to have dynamical evolution from a pure state to a mixed state. So if this semi-classical picture is right, that's just what happens. So could this semi-classical picture plausibly be wrong? Or, you know, what could be wrong with this picture that I've drawn? Well, I've divided up into 4 places, possible places where this picture could be wrong. Maybe it's wrong at the formation of the black hole itself. Maybe it's wrong during the long period of evaporation of the black hole. Maybe it's wrong at this final burst. And maybe it's wrong in its description of the singularity and what is going on, you know, after the singularity, if there's no, I mean, or after what replaces the singularity. I guess if the singularity is there, there's no after particularly. But if the singularity is replaced, there could be. So let's look at these in turn. So this possibility 1 is that you never form a black hole. And this is the scenario that advocates of fuzzballs would believe. So the idea is you form, it looks just like you form the black hole, but then somehow, just as you're getting very close to forming the horizon, and of course it really better be very close, or otherwise if you noticed way before the collapse, well, that would be producing, you know, before the black hole collapse, you'd be in danger of modifying gravity in places where you can test what's going on. And if you didn't have something that looked like the exterior of a black hole to pretty close to the horizon, you'd have lots of issues explaining why things look like black holes, et cetera, or at least you might. So in this scenario, sort of just before you form the black hole, you tunnel into something else that's completely non-singular and doesn't have a horizon, so this red dotted line isn't there, and you have some strange stringy-ish state or whatever that then persists forever and somehow or other does some mock-up of Hawking radiation, but the state is, you don't have a, point is you don't have a black hole and the state is pure. Well, I mean, this is an incredibly radical alternative, and, since this is could be a very macroscopic body and low curvature regime and all that, you need a major breakdown of classical general relativity as well as quantum field theory in a really low curvature, low energy regime. And one of the things I liked in Bill's talk at Santa Barbara is his F equals ma estimate of what you would need to kind of stop this huge solar mass or more object that's collapsing at about the speed of light, to just suddenly halt that and go into some other kind of configuration. Another thing to note is that, whatever is deciding to do this tunneling or whatever has got to really act quickly and precisely. If you wait too long to form the fuzzball, it's way too late. You've already made a black hole, and it doesn't really matter what you do with the rest of the stuff inside the black hole, unless you want to get some major violation of causality, et cetera, also in a low curvature regime. So I think this is by far the most fantasy-laden version of what might go wrong. Yeah?
So can this be paraphrased by saying that according to this proposal, there is never even an apparent horizon?
Yeah, that's right. There would not even be a...
The diagonal dash line would be the apparent horizon in what we all believe is the standard Schwarzschild solution for a large collapsing star. Yeah,
so I mean, it amounts to assuming that the collapse halts at some incredibly small epsilon outside R equals 2m plus epsilon for some incredibly small epsilon and goes to some non-singular state there. Okay, well, another possibility is that you actually have major departures in this regime where the semi-classical theory would say that you're very nearly a Schwarzschild black hole, you're just very slowly losing mass in accord with the energy that's being radiated away to infinity with the Hawking radiation. So this is also a really radical alternative because, again, you need to sort of destroy this entanglement, this short distance entanglement between the inside and the outside of the black hole in, again, a really low, if you make the black hole big enough, you have to do this in a as low curvature regime as needed. And as of course, breaking the entanglement is going to make, make the state singular where you've broken the entanglement, as I was explaining earlier. That's the firewall, right? That you're converting the horizon to some sort of singularity in this low curvature, highly low curvature regime. Another point, that's why I call this very radical. Another point, though, to make is that you certainly have to do this, something like this, to avoid the entanglement. It's far from clear that just declaring firewall or something is going to be in any way sufficient to get you out of the trouble. Again, I could have produced entanglement between the stuff here and stuff way out there, which would result in entanglement between here and here, presumably at this later time, you've got to also do something about that. And I'm not sure how the firewall helps with that. The firewall may help you with avoiding entanglement between the Hawking radiation and the stuff going into the black hole while the Hawking radiation is going on. But anyway, so even with this kind of radical alternative, you're not by any means out of the woods in terms of explaining how you might end up with a pure state. Okay, so now the third possibility is that something goes wrong at this last little bit of the evaporation, the sort of, when you've evaporated, if we accept that you formed the black hole and you evaporate in a normal manner down to presumably something of Planck scale, maybe then quantum gravity takes over and semi-classical theory is wrong, and you don't evaporate the rest of the way, and you're left here with a remnant, and the remnant keeps keeps track of all the entanglements that you ever had before. I mean, again, the black hole doesn't evaporate. The singularity, I don't know where to draw the singularity, but anyway, any later time slice you can have come in through the remnant, and it's still a pure state. So this is not a radical alternative. I mean, because you're talking about a breakdown in a regime where you'd expect semi-classical gravity to break down, but it isn't at all clear to me what good this does you. I mean, to say, on the one hand that the black hole is evaporated completely and the information is lost in this sense, versus the information is not lost, but it's contained in this Planck scale remnant, and you can't possibly have any access to it. It doesn't seem to me like a huge difference. And so if I tell you there's a remnant, then you're happy. But if and as a remnant, you'll never see it, you'll never be able to do anything with it, you're happy. But then if I tell you, and actually the remnant isn't there, then, this is a disaster for quantum theory. I don't really understand that reasoning. A further argument, and this is the one that's most prevalently used, is that, of course, this remnant might be a remnant of some huge black hole, in which case it would have to have a huge number of states to purify the Hawking radiation, et cetera. But then you would think this object would have huge entropy, and if it had huge entropy, it has very little energy, just Planck mass kind of energy, presumably. So it would be presumably thermodynamically highly favorable to form these things, and you'd think the vacuum would be unstable to forming lots of these remnants that have huge entropy or something. So that's what I'm referring to with the thermodynamic problems. And in fact, although remnants have been mentioned from time to time, and there have been a few periods in the 1980s that I can recall where they were popular, I don't know of any present advocates of the remnants, but at least that's not a radical alternative.
Bob, when you say there's a problem, isn't it a perceived problem more than a real problem?
So you mean, are you talking about the thermodynamic?
So if there's all things which contain a lot of entropy, we might not know exactly why it has that sort of high entropy.
Well, no, I think the argument is that really just that it would be favorable, if we have 10 Planck energies available in some box, it would, rather than have a little bit of very low energy radiation in the box, you'd get much higher entropy if you had a bunch of these remnants that each of which had a lot of entropy. So you might argue that there ought to be some tunneling process, and basically things would be. I don't want to argue this. There is an argument there. It would be hard to see how you wouldn't assign large entropy to remnants. in the scenario, and that does seem to be problematical. But the main argument I would stick with is I really don't see, well, how this does you a lot of good to say it's there, but you can't see it, versus it isn't there. Doesn't all make that big a difference to me. Yeah.
Yeah. So, in spite of what you just said, I still want to push this point, because it seems to me that the thermodynamic problems are mostly problems of analogy. So you have the subject of a lot of entropy, and maybe it could be unstable, but until you understand the remnant as a point gravity object, you don't know that it would lead to instabilities of flat space. You don't know that it can pair create, and you don't know that.
Yeah, I agree, but it's not a tremendously, overall, I think it's not a tremendously attractive alternative. And furthermore, I don't know of anyone who's, I can tell you advocates of fuzzballs, I can tell you advocates of firewalls, but I don't have any names to mention in terms of present advocates of remnants. So, no, well, but it might be a good reason to move on and not discuss it further or something. But, I mean, okay. And then the last possibility is that you don't really have a singularity, and in some sense you don't really have a black hole. Here in this scenario, you do have an apparent horizon, and the thing looks just like an evaporating black hole down to, Planck scale. But then everything that was inside the black hole that you thought perhaps had gone into a singularity, or maybe had gone into a baby universe, or maybe had done something else, actually comes out. And in that case, automatically the final state should be pure. So the problem with that is that this would allow, again, using the word information sloppily, but an arbitrarily large amount of information. There'd have to be a lot of, arbitrarily large number of quantum states in this thing, that to be released from an object that, is physically, from the external observer, just an object of Planck mass and size. Now, I would say this alternative is not as ridiculous or crazy as as I would hope it should at least initially sound, and which is also why I don't think there are any advocates serious advocates of this alternative. But there's a very nice a recent paper of Hote, Schitzold, and Bill, looking at a model of an accelerating mirror with the acceleration adjusted so that it emits radiation that looks just like Hawking radiation. And in this case, there are, just as in the Hawking effect, some corresponding partner particles to the Hawking radiation. Instead of going, traveling along just inside the horizon, as in the Hawking case, these things are traveling along just outside the mirror. And while the mirror is in this state of acceleration, there's no real distinction between them and vacuum fluctuations. But now if you stop the acceleration of the mirror, but don't slow it down, these partner particles will reflect off this now inertial mirror, and they will carry away then all the information, but effectively they'll be hugely redshifted, reflecting off the mirror, and they'll actually carry off extremely little energy. So they'll do exactly what you'd like the burst to do. It seems to me, though, it would be extremely difficult to have any behavior like this in the black hole case, where you've got conservation of energy, more severe conservation of energy type restrictions. Unless you have some sort of highly non-classical burst region that lasts a long time and is of large size. I think this is worth, for the people who want to get a pure state at the end, I would think this alternative would be worth looking at a bit more closely to see if there's some good way of doing this in the black hole case. As I say, I think there is a good way of doing that in the mirror case. But again, I don't know of any present advocates of bursts, which is not to say that they're wrong. Right, I'm setting things up. What I'm doing at this stage of the talk is just, we've got a semi-classical picture that predicts pure states go to mixed states. What could be wrong? Well, I've looked at all 4 regions and tried to give an idea. Yes, Bill?
Well, there are at least 2, maybe 3 advocates which are Stephen Hawking.
Hawking?
Yeah.
Oh, yeah, okay.
His talk at that meeting, and he's written that up.
Yeah, that's right. And I guess Bardeen.
Jim Bardeen.
That's right.
And maybe Valeri. I don't know whether you would describe yourself as an advocate of the burst scenario.
So the answer is yes.
The answer
Okay.
is yes.
Okay. So I stand corrected on that point.
But I guess maybe I can point on that. So I guess that one reason why number 3 and 4 might not be as popular is that they violate the area law, that you have more entropy than the area in those regions.
That's right. Yeah. Okay. So anyway, so why are people? So now let me get to the issue of, so why are people wanting to go to the lengths that you would need to go to, as I've described, to avoid the conclusion that a pure state goes to a mixed state? What are the arguments against information loss that would cause people to go to such lengths? So let me now, so that's the last part of the talk. Let me discuss that. So as far as I'm aware, there have been 3 major arguments advanced to that information can't be lost in this sense, and therefore one should go to one of those, at least one of those 4 alternatives that I've been discussing. So the first one is referred to as violation of unitarity, and it's always seemed to me that there's been some fundamental confusion in the way this is used, because the word unitarity in quantum mechanics has 2 very different meanings. You could say that you violated unitarity if you violated some conservation of probability. What is meant here, though, is what I've been describing, evolution from pure states to mixed states, without any problems with making probabilistic descriptions and being completely just, all the probabilities add up to 1, et cetera, in this situation. So if we were talking about the failure of conservation of probability, that would be a big breakdown of quantum theory. It would even be a breakdown of logic, and we'd have to find some way of fixing that. But that's not what's being proposed. What we're talking about here is just this evolution, a breakdown of evolution of pure states to pure states, that is, having pure states to mixed states. And this is something that you always will have in quantum field theory if your final time is not a Cauchy surface. And I claim it's totally innocuous. And the example I like to give for that is, in Minkowski space-time, consider the evolution of, let's say, a free massless Klein-Gordon field, starting from some usual hyperplane Cauchy surface and asking what the final state of it is on a hyperboloid. And the claim is that because this so this is a completely well-defined problem. I can tell you, probabilities for any observables you want up here on this hyperboloid. And probability will be conserved. But the point is that the state on these observables will be mixed because this is not a Cauchy surface. There's radiation. I mean, this can be the vacuum state, but there's still, radiation, quantum field degrees of freedom that are propagating off to null infinity. And the point is those degrees of freedom are entangled with the ones that are getting caught by the hyperboloid. And the state up here will therefore be mixed. So you have evolution from a pure state to a mixed state. This is a prediction of quantum theory. It's not in any way a violation of quantum theory. And the pure to mixed state of evolution that's predicted by black hole formation and evaporation is just completely the same character. So, I mean, I don't see why one should be any more upset by that than one would be upset by what I just described. Now, I find it really ironic that a lot of the same people who consider this the evolution from pure to mixed that you'd have in black hole evaporation, they consider that to be a violation of quantum theory, whereas I claim it's just a prediction of semi-classical quantum theory. Maybe it's wrong, maybe quantum gravity makes corrections, but it's a prediction of a quantum theory, so it's totally consistent with quantum theory. But then those people endorse really drastic alternatives like firewalls, et cetera, that really do violate, or quantum field theory at least, as we understand it, in a regime where everybody would have thought, you know, a priori that quantum field theory ought to semi-classical gravity and with quantum field behavior of the fields should be an excellent approximation. So I want to say that I believe very strongly in the laws of quantum theory, you know, on length scales where presently understood quantum theory ought to be valid. And I pledged in Santa Barbara, I'm going to pledge again to vigorously defend quantum theory against the people who might well have initially set out with good motives to try to do something positive for quantum theory and somehow got diverted into doing things that are trying to destroy quantum theory as we understand it. Okay, a second class of arguments against information loss concern problems with conservation of energy and momentum. And in fact, I mean, from the mid-1980s until the late 1990s, this was by far the most highly cited reason for believing that pure goes to mixed. You know, there was a problem with that. It couldn't happen, and we have to, well, we had a black hole information paradox that we had to resolve in terms of figuring out how information gets out. So in particular, I mean, these are not the only authors who did this, but they're by far the most prominently cited. They wrote by far the most prominently cited paper that you would have problems in this case. But they were considering only a particular type of evolution law, taking pure states to mixed states, a Markovian kind of thing described by the Lindblad equation. And this wouldn't be, first of all, a good model for what one would be expecting to occur in black hole evaporation, where the black hole clearly retains a memory of what it previously emitted, and you know, this kind of Markovian process wouldn't be appropriate. Now, going along with this, I mean, there seems to be a pretty widespread belief. I mean, I'm not really in this area, so I'm not sure I can say firsthand, but about what's widespread or not. But that you know, if you're going to do any decoherence, that involves energy exchange, and that's going to result in some failure of conservation of energy, or similarly momentum. Well, I mean, if you take an environmental system, modeling it with some sort of thermal bath of oscillators, that is true, and this Lindblad equation is, you know, at least in appropriate circumstances, a good description in that case. But if your environmental system actually has a lot of states but doesn't carry a lot of energy, something you might picture as a spin bath, then there's no problem causing a lot of decoherence without a lot of energy violation. And in any case, I mean, these general statements apart, Bill provided a few years ago a really nice example of a quantum mechanical system that interacts with some, what you might call, hidden spin system in such a way that this quantum mechanical particle has evolution from a pure state to a mixed state, but energy conservation holds exactly. So the bottom line is that there's not a problem of principle with maintaining exact energy and momentum conservation in quantum mechanics in an evolution where a pure state goes to a mixed state. Okay, the final argument, major argument that has been invoked, which by far has been the most popular argument in the last 15 years, involves this so-called ADS-CFT correspondence. So a one-sentence version of what the ADS-CFT correspondence, well, a one-sentence argument that you can't have information loss based on this ADS-CFT correspondence is a statement that ADS-CFT tells us that gravity, at least in asymptotically ADS space-time, so we'll change the arena to just be considering black holes formed in asymptotically ADS space-times, that is dual to some conformal field theory, but the conformal field theory doesn't admit evolution from a pure state to a mixed state. And since these theories are equivalent, then such evolution can't be possible in quantum gravity. So you must end up with a pure state, and you can't have information loss. Now,
of course, that not answer your objection to the remnant proposal? I'm conjecturing what these people would say in response to your poo-pooing the remnant.
Well, the people, all I can say is the people arguing for this are not particularly arguing for remnants, and would typically endorse the argument that the thermodynamics is wrong and their entropy should be 1 or 0 or 1 or something, rather than the huge entropy you'd need to have all these states. Okay, so this is by far the most difficult objection to answer, because the argument is, I think, being made in a kind of loose conglomeration of ideas that I find very hard to pin down. So the first point is that, of course, this ADS-CFT is a conjecture. The problem that I find in trying to deal with the arguments is not that this is a conjecture that hasn't been proven. The fundamental problem is that this is a conjecture that, to my understanding and knowledge and what I can learn asking people and talking to people, it just hasn't been formulated with the degree of precision that I think you'd need to make some reliable use of it in this kind of argument. So let's look at that a little bit more fully or carefully. So if I want to make the argument for information loss or no information loss based on ADS-CFT, so what do we really mean by information loss in black hole evaporation? So we're saying that we can create a situation that if we look at the bulk observables at late times, those are not the complete set of bulk observables. Namely, it's excluding all the observables corresponding to what went into the black hole, which then evaporated. I mean, this is really what's meant by information loss, that the late time observables are not all the observables of the system. That's why the state is mixed, because those observables are entangled with other observables of the space-time system, but they're not present at late times. So at least people usually say, as best as I can tell, who are advocating the ADS-CFT, that if you look at the complete set of bulk observables, that should be in one-to-one correspondence with the complete set of bulk observables in an ADS space-time. That should be in one-to-one correspondence with the complete set of CFT observables. Now, the CFT observables are supposed to undergo ordinary Hamiltonian evolution. So the CFT observables, certainly at late times, or for that matter, at any finite time, should be equivalent to the complete set of CFT observables. Right, you have Hamiltonian evolution of the CFT observables, so if you know them at any one time, you know them at all times, or in particular, if you know them at late times, you know them at all times. So if the bulk observables, let me try to get this, the argument that I'm trying to make now state. So with this established, if it were true that the bulk observables at late times were in one-to-one correspondence with the CFT observables at late times, then the CFT observables are at late times are all the CFT observables, but all the CFT observables are all the bulk observables. So arguing this way, we would the AES-CFT correspondence would certainly suggest that the bulk observables at late times have to be in one-to-one correspondence with the bulk observables at all times, and in that sense, which is the appropriate sense to be using, information can't be lost. So in terms of, so what's weak about this argument? I can't say right or wrong because it isn't being made in some way where you can easily say this statement is right or this statement is wrong. But the problems, as I see it with this argument, is really, first of all, very little is known about this conjectured dictionary between bulk and CFT observables. And indeed, that's a truly major problem in quantum gravity. It has been since before I was a graduate student, and the situation has not particularly changed as far as I can see now in terms of a priori saying what bulk observables are in quantum gravity. There's this whole major so-called problem of time, that the bulk observables in quantum gravity should commute with the constraints, but that basically is telling you time evolution of observables is well, the commuting with constraints is essentially telling you, via the Wheeler-DeWitt equation, excuse me, that observables that would depend on time are not legitimate bulk observables, because anything that commutes with the Hamiltonian constraint or and classically has vanishing Poisson bracket with the Hamiltonian constraint is invariant under time evolution. So anyway, I'm saying there's a major problem conceptually of just what you mean by bulk observables. So it's going to be hard to produce a dictionary between these CFT observables and what are supposed to be bulk observables. So I don't know how one can understand this correspondence so well to be able to, for example, say that the CFT observables are in one-to-one correspondence with all the bulk observables, including ones representing observables inside the black hole, versus they are only in some one-to-one correspondence, let's say, with the space-time region outside of black holes.
I can answer that.
Okay.
Horizon is not a quantum gravitational notion, so I guess this doesn't make any sense. If there is an exact quantum correspondence, cannot separate between inside and outside the horizon because that's only a semi-classical notion.
Right, but I mean, we're trying to, when we're talking about black hole formation and evaporation and information loss in that process, I don't know how to talk about that even without some semi-classical notions applying.
No, but
so,
and then it has a deeper problem. That is, it would mean the CFT would be incomplete. Right? So
the CFT would be incomplete if that were true. You're losing degrees of freedom from the CFT, and we say, and of course, if we know enough about that, no, that's not true.
Well, the CFT,
Well,
the bulk.
but I'm not talking about anything having to do with the CFT. I'm assuming that's totally known and understood, which I'm not completely sure that's even a justified assumption. But let's assume that everything is known about the CFT. What I'm concerned about is the correspondence that's supposed to occur between CFT observables and bulk observables in quantum gravity, which sounds like a really difficult issue given that I don't have the foggiest idea what bulk observables are in quantum gravity. So, okay. So a second question that I would ask is, I mean, is this correspondence between bulk observables and CFT observables supposed to be local in space-time? In other words, do you get the corresponding CFT observable by taking some limit of a bulk observable as you go to the ADS boundary? Most arguments that I hear are assuming that either explicitly or implicitly, and many people, when I ask about that, deny that that's the case, that this, say that this should be called the dual CFT theory, not, you know, one shouldn't use the word boundary because there isn't a naive correspondence between bulk observables and boundary observables. It's just there's some abstract association. Yeah, I'll take a question, but I won't answer it.
Even if what you say is true in blue, the CFT observables only correspond to observables outside the black hole, you still have a problem because initially it's pure outside the black, there's no black hole, and then afterwards it's...
Yeah, okay, so I'm not saying that this would eliminate, yeah, that's a very good point, and I will respond. Yeah, so I'm not saying, if this were true, that wouldn't solve the problem, which is, I think, what you're saying. I mean, if it were true that the bulk observables only corresponded to things outside black holes, you'd still, you know, if the, well, okay, this wouldn't, a positive answer that this is only observables outside the black hole would not say, okay, that resolves any contradictions. Okay, there would still be a contradiction.
5 minutes.
Yeah, I'll be finished. And this is one more slide to go after this, and I'm all done. Right. So, but I'm just, you know, I mean, the arguments are used in such a way that you know, there's just a correspondence of observables. It's not clear to me what the right, you know, what evidence is there that the correspondence, you know, is not. I'm just raising the question about how well is this correspondence understood. That's all I'm intending to do in this. Okay. So getting back to this, if it's local in space-time, as people seem to assume, then that leads to an issue that I think is much more paradoxical or problematical than anything with the information paradox, which is that would, if the correspondence really was, you know, bulk observables near the boundary correspond to the CFT observables at that time, then that would apply that if you knew the bulk observables near one cross-section, near in space-time, to one cross-section of the CFT boundary, well, then you'd know the CFT observables at that time, but then you'd know the CFT observables at all times, and then you'd know the bulk observables at all times. And that's totally at odds with what is the case in classical general relativity, which is that knowing all the observables in the neighborhood of a cross-section near infinity at one time can't possibly come anywhere close to telling you about the observables in the interior, and therefore can't tell you anything much about the observables at later times. So I think that would raise a lot of issues much more significant. If there is this local in time correspondence. On the other hand, if it's non-local in time, then I don't understand why the CFT at late times might continue to encode the information that went into the black hole, even though that information is no longer available to the late time bulk observables. Anyway, the point is that it would be nice if these ADS-CFT ideas could be developed further so as to make a really solid argument for or against information loss. And I claim we'll know that such a state has been reached where there's a really solid argument. We'll know that when the argument, not only tells us that information has to be regained, but explains to us how that information is regained. Where in my space-time diagram do things go wrong? Or, is it even some place other than I mentioned? If it's just going to be an argument that somehow or other information has to be regained, I'm never going to be comfortable with this argument. And until this thing is done, I'm going to stick with believing in information loss. Okay, thank you.
So
yeah.
You claim that you want to defend quantum mechanics very rigorously, but at the same time, argue you're denying quantum tunneling, which is a fundamental part of quantum mechanics.
No, I mean, I believe in quantum tunneling. It's totally derivable from completely causal physics.
Absolutely. But you agree that you cannot locally, by perturbation theory around from a classical state, you cannot predict the tunneling from that from a classical state will happen or will not happen.
Well, I don't know what we don't have a better theory, a quantum gravity theory, but I certainly believe there are plenty of non-perturbative phenomenon in quantum theory which you cannot get by perturbing.
The criterion that quantum gravity could only be important when curvature becomes Planckian. That's basically ignoring possibility of quantum tunneling, because tunneling, you can never write a local criterion or perturbative criterion for tunneling.
Well, but the quantum tunneling presumably would take place in this might still take place, but would take place with incredibly low probability. And that wouldn't, how is that,
Well, but you could do this calculation, and that's what Matthew argues for. You could do this calculation as you forming a horizon, or you would be, and then the tunneling rate, there is no exponential separation because you have exponentially many states that you could tunnel to. If you believe in the area.
So you're arguing that the semi-classical we can break down a regime where we both believe that.
Yeah, right. That's what I'm saying, right. Right.
And I'm saying that's quantum mechanics. Quantum mechanics does tell you that's tunneling.
No, but quantum mechanics doesn't. Well, you go ahead.
Quantum mechanics is magic, and magic can do anything, and therefore quantum mechanics.
No,
that's your argument.
No, you can do calculations, and
there's just look. You look at the system. Your curvature scales of kilometers, where you damn well know you understand the physics, and in that scale, there's Einstein equations are violated to orders of e to the 10 to the 80th.
But just playing
no
with
tunneling in quantum mechanics is going to do that.
Absolutely. If you count the number of states that the black hole would have, it's exponential of the area. And yes, every tunneling.
I'm saying the energy that you lose, that you change there, is of the order of e to the violate energy conservation of the order of e to the 10 to the 80th. You need stresses that are e to the 10 to the 80th times the energy density.
No.
Yes.
No.
Yes.
Okay. You don't.
It seems we're not resolving this issue. Perhaps another question? Yeah, Ted?
Just wanted, you talked about the matter collapsing might have been entangled with something else, and you also would need to get that information out. I'm just wondering, what if the matter is in a pure state? Isn't there also a question there, recovering what pure state it was in as information?
Sure. No, you have the situation where the matter, the collapse is sort of matter in a pure state or whatever. Of course, the quantum field is never really in a pure state because it always has at least vacuum level entanglements, which is enough to produce the Hawking radiation, or which is related. But so, I mean, I think the usual, I'm pointing out that the problem is worse than just the vacuum entanglements, because you could have macroscopic matter entanglements too.
But I don't understand, like, why wouldn't it also be worse if the matter was macroscopic, a pure state?
Well, you'd have the same problem that everybody is talking about. Let's say, I think I'm not making this clear.
So it's
maybe
not making it any worse unless I entangle the matter with something?
No, well, what I'm trying to argue that it would be worse because you'd have correlations down here with stuff here, and it's hard to see how putting a firewall over here is going to help do anything about that unless you... But
also, how would a firewall help get the pure state information out if the matter that collapsed had been in a pure state?
Oh, no, I'm sorry. Okay, so you don't get the information out on the pure state, but you have a pure state still out here, and people are then happy for some reason. I don't know. I mean, I don't know what the problem is with the mixed state, and if people, it seems that people would be very happy if they had a pure state out that wasn't entangled. I mean, if just because you've lost, yeah, I mean, you're saying there are two problems. I mean, one is you've lost degrees of freedom in this system. That's what you're saying. There was some pure state describing stuff here, and that isn't reflected here. I don't think there's any way of getting the information about the original pure state out. And yeah, I think maybe that's sort of, that sounds to me a little worse than having overall than the additional idea of there being some entanglement between, this not being a pure state and there being some entanglement. But people seem completely focused on the entanglement issue, and nobody, I don't think I've ever heard anybody raise, as you've just now, the issue of kind of loss of degrees of freedom of the system.
I just have a comment. I think you're really right that the sort of playing ground of the debate has shifted over time a lot. And right now it's sort of more shifted towards, in my view, the thing you concluded on, which is namely the challenges to ADS-CFT now to understand itself. Something seems inconsistent about ADS-CFT, and that's actually, I think is the most interesting version of this debate that's come up yet, because it has the potential of evoking a deeper understanding of the duality, if the duality indeed is correct. Than whereas previously it was, you could just disagree forever about things. So
I think they still can.
Fortunately, we have to stop here. Let's thank Bob again for this
Okay.
very clear introduction.